Okay, let's solve this LeetCode problem, minimum obstacle removal to reach corner. We're given a 2D integer array, and each cell has one of these two values, either 0, it is empty cell, and or 1, which represents an obstacle. An obstacle may be removed. We can move up, down, left, or right from any cell to another cell. And we're asked to find the minimum number of obstacles to remove so that we can reach from the bottom, from the top left corner to the bottom right corner. So from basically the corner 0, 0 to the lower right corner m-1, m-1. In this example, they remove these two obstacles to reach the bottom right corner. After you remove these two obstacles, this is the state of the grid, and you can follow this path to reach the bottom right corner, lower right corner here. So in this case, the answer is 2. If you look at this one, you do not need to remove any obstacle. You can just follow this path from this one, the middle, and then go up and down to reach the lower corner. Now let's see how we can approach this problem. Okay, let's look at example 1. In example 1, they remove these two obstacles to make this path here. So just to be clear, let me use another color. So this is the path they create, so by removing these two obstacles. So how do we approach this problem? Since we can move right, left, and up and down, let's try to do something about this moving. So if we're given this grid and it says that you can only move right and down, basically this way and this way, then you might want to think about DP. You might want to solve this problem with dynamic programming, because then you would want to reach this bottom right corner. Then there are two ways to reach this bottom right corner, from above and from left. So then you have to, so in this case, when you go to this bottom right corner from above, then you're dealing with this sub problem. And in other case, when you go from left, you're dealing with this subgrid here. So you have clearly subgrids, you have clearly sub problems. But our problem is not with 2 directions. We're given 4 directions. In almost all cases, when there are 4 directions, depending on the problem, this is out of the scope of DP. We cannot solve this problem probably with DP, because the managing state is too hard in this case. You cannot see clearly what you should do, because if you're in the middle, let's say here, what are the cases? What are the possibilities? You can come from above, you can come from below, you can come from left and right. So you see the transition here. There is this part, and there is this part, and this part, and this part. So it is not possible to use in this case the DP, because we cannot because we cannot find the optimal structure here. So if that is not the case, we're given this grid. So most of the time, and we're doing some sort of movement, and we're doing some transition from somewhere to some other one, right? And maybe we can model this as a graph. So what I mean, let's just say these cells are the nodes in a graph. So in this case, we have 9 nodes, and every pair of nodes, every nodes are connected. So this connected to this one, this connected to this one. So basically, just like the grid, we create the graph. Just to be clear, so you don't have to create the graph. So then we have some special cells. Let's just color them in red. So just to make them obstacles. So these are obstacles. So we mark them in red. So we're asked to find the minimum number of something. So if you're dealing with a graph, what could it be the minimum? So it could be the minimum distance, or the shortest path from a node to another node. You see, we have two nodes. We need to reach from this node, the bottom here. So we have two nodes. What if it was about finding the shortest distance in a graph? Well, it is not, but we can transform this problem into such problem where we're dealing with the shortest path. So we're basically finding the shortest path in a grid, in a graph, to find the minimum number of obstacles that need to be removed. Now, how do we do that? When we move from this cell, this is an empty cell, by following this edge into this cell, there is an obstacle. So this adds a cost of 1. This has a cost. When you're given a graph, in traditional sense, graphs are not always about shortest path. You might given like a graph, and they might ask the shortest path. You can interpret this shortest path idea, this notion of finding the shortest distance from a vertex to another vertex, in a different way. And the graphs are a powerful data structures. This vertices might mean a lot of things. They might mean it might be a state of a problem where the graphs are actually in disguise. You cannot see clearly how you can model it as a graph, but it is possible. So, and this edge might mean any sort of relation. So, and it has some weight. This weight can be cost of reaching there. It can be the time. It can be the distance. It can be some other thing. It is the cost of this edge. So in our case, the distance. So you can think of this graph as distance. We're finding the shortest distance. But this meaning is that if we follow this edge, this is a cost of 1. What do we mean cost? Cost is the number of obstacles we remove. So basically, if we move by following this edge, we have to remove 1 obstacle because we're running into a cell where there is an obstacle. So then if we follow this one, there is actually another obstacle. So that's a cost of 1. So to reach here, we have a cost of 1. And to reach here, we have a cost of 1 by following these two edges. So let's go back up. So we have a cost of 1 here to cost of 1 here. Here we start at this one, so the cost is 0. Now from this point, so basically whenever we run into an obstacle, then this is a cost of 1. Basically, the edge that we followed to reach this cell, any cell with an obstacle, it adds a cost of 1. Basically, this is the weight of this edge. And we have to find, if we're moving, for example, from this one to here, this is a cost of 0 because we're moving into a cell where there is no obstacle. So this does not add any cost. We can freely move there and not remove any obstacles. So we have to find the shortest distance from the starting point to the ending point, to the destination, where we define the weights of the edges as how we move to obstacle, as if we move to obstacles or we move to empty cell. If we move to an obstacle, then this edge adds a cost of 1. Otherwise, if this is an empty cell, then this edge adds a cost of 0. So in this case, we have to find the shortest distance on a weighted graph, which in this case we can use Dijkstra's algorithm. In this video, I will not get into Dijkstra too much because I don't want to keep the video too long. So let's just go over this example with the Dijkstra. So we move this here. This is a cost of 1, and we move to this cell. This is a cost of 1 again. So in Dijkstra, we know that we start at a node and explore all of its vertices and update adjacent vertices. Let's say we're here and we move here. The cost is say x, and we move each one of this adjacent vertices and update their cost. For example, the weight is here, the W1. If x plus W1 is less than the cost of this one, then we update it and push it into our queue to process it later. Otherwise, we don't do that. Otherwise, we do not update the weight. So that is the basics of Dijkstra. When every time then we grab the vertex with the smallest cost or the shortest distance from the starting point. That is the core of Dijkstra, but of course it needs its own video because we need to see the correctness of this algorithm. But for now, let's just focus on this problem. So we have a cost of 1 and we have a cost of 1 on this one. So the shortest, basically the lowest cost in this case. Let's think about the cost instead of shortest distance. So we find the minimum with the minimum cost, and we have 2 of them. It doesn't really matter in this case. So we grab this one, and now we follow this 2. This has been visited. We're not going to follow this. So then we follow this edge here. So we see that we come into a cell where there is an obstacle. So this edge must add a cost of 1. So we have previously a cost of 1, and this adds a cost of 1. We update, we haven't visited it, so the cost is going to be 2. And we move down here, the cost is also going to be 2. We have 1 here, plus 1 this edge, because we're running into a cell where there is an obstacle. This is 1 plus 1, 2, so we have 2 here. Now then from this one, we can go here, but this is 1 plus this edge, because it adds a cost of 1. This is 1 plus 1, 2. It's already 2. It's not less than 2. We do not update anything. And we go down here. This is going to be a cost of 2 as well, because we're running into a cell where there is an obstacle. So now we have processed this 2 cells, and this 3 cells. So now we have these ones in our possession. So from this, since all of them have the same cost, we can just grab any one that there isn't the one with the smallest cost. So let's just say we grab this one. We're not going to visit this. This is already done. It has its shortest distance. Then we visit this one. Since we're moving into a cell where there is no obstacle, it's empty, we do not have to remove any obstacle. So this does not add any cost. So this weight here is 0. So 2 plus 0 is 2. So we add here 2. The cost of reaching this cell from 0 is 2. We're just removing this 2 obstacle. And then we grab the next one. It's 2. So from this, we're not going to move here or here. We only move right. So right is 2 plus 0 again. So since we're moving it into an empty cell, this adds a cost of 0. So 2 plus 0 is 2. 2 is not less than 2. We're not updating anything. We go down. We haven't visited this. So initially it has the maximum, the infinite. Since we're finding the minimum, the smallest cost. So initially it has the infinite cost, so it's too large. So basically we're updated. So it's 2 plus 1, because this edge has a weight of 1. We're running into a cell where there is an obstacle. So this is going to be 2 plus 1, 3. To reach here, we need 3. We need to remove 3 obstacles. And then we have this one. So from here, we're not going to move here. We're done with this one. We're going to move here. It's going to be, this is also 1. So 2 plus 1 is 3. And so 3 is not less than 3. We're not updating anything. So then at the end, we have this 2 here. And we grab the smallest one. It is 2. From 2, we'll move to bottom right corner, it's the cost is going to be 2 plus, because this is 0. So we have 2 here, and from then we grab this one from 3 to 0, from 3 to this empty cell, this adds 0. So 3 plus 0 is 3. 3 is greater than 2. We're not updating anything. This makes it worse otherwise. So we have 2 here. So if then after that you have 2. So in fact, you can now move to 3, because from this one, if you're asked what is the minimum number of obstacles you need to remove to reach this point, it would be again 3, because if you move from this one here back here, so this would add a cost of 1, so it's already 2. 2 plus 1 is 3. So you don't do that anyway, because this has already its shortest distance, or the minimum cost. So basically we're done. We now have the cost, the minimum number of obstacle removers to reach every other point from the source, from the bottom, from the top left corner. And we need only this one, since we require to find the bottom right corner. So it is 2. So in this case, the answer is 2. So as you can see, in this problem, we model the given given problem as a graph. So remember, in a graph, in its natural form, so we learn about the vertices and edges and what they mean, and after that there are some weights, and on a weighted graph we learn about the shortest path. But it does not necessarily have to be about the shortest path. The shortest path, well, it is shortest path, but when you find the shortest path, it depends on how you define this weight and the relationship between this. It could be the minimum time between these two vertices. This could be cities, and visiting these two cities, for example, it might be 2 hours. So when you at the end, if you solve this problem, if you find the shortest distance from, for example, this one to this city from A to B, you actually find, yes, you're finding the shortest distance in a graph with a shortest distance algorithm, but you're finding the minimum time to reach B. So it's about how you define your nodes, how you define your vertices. This could be a single vertex without any meaning. It could just be a city with a letter, or 0 or 1, 2, 3. Or it could be more than that. It could be some sort of state. It could be like the coordinate of something and some other variable k, which shows, some sort of state. For example, coordinate of this could be like x plus 1, y, and k minus 2. Some sort of state it shows. It's about how you define your nodes, and then how you define these edges, because there are the relationships. Then you have a beautiful graph, you have modeled your problem as a graph, then you can look for some graph algorithms, maybe shortest path, I don't know, maybe minimum spanning tree, to solve your problem. And then interpret what they actually mean. In this case, the shortest path, when you find the shortest path, you're finding the minimum number of obstacle removals. So it's important to look for the graphs when you see something like this, a grid, and you're moving in all of the directions, and you're asked to find minimum number of something. So the next time when you see something like this, try to think of graphs, and maybe you can solve it this way. Now let me show you the code, and there I will explain a little bit of Dijkstra. We have the directions when you're given a grid, so you might want to have these directions. They will represent right, left, down, and up. And then we have the grid M and N, and process. I will use this process is basically when we're done with a node or a grid cell, we're just going to mark it process so that we never ever process it again. So in this case, the process is 2. I'll use the grid itself to mark the cells as as processed instead of creating another process grid. So in this case, in our grid, we originally have 0 for empty cells, 1 for obstacles, and now I have 2 for, so just to mark for this cell as processed. Then we have the priority queue. So by default, this is a max heap in C++, but I will push the negative of the distance or the cost, whatever it is, to the priority queue. So this will actually give me the effect of finding the minimum distance. So then we have the cost to the cost matrix, the cost grid of the same dimension as our grid. Then the cost to 0 to 0, the cell 0, 0 is 0. Then we push into our max heap. It's actually will be min heap. The distance to 0, cell 0, 0. These two are the row and column of this cell. And then as long as we have something in the queue, we grab it and we take the row and the column so that we can find the current cell. And if we have processed this current cell, we can continue. Otherwise, we mark it as process. Then we try to go in all 4 directions. And if some of these directions is not valid, maybe they are outside of the grid, or we have already processed this cell before, so in this case we skip this, we continue with the next iteration. Otherwise, then we have the cost of reaching the row, the new row, plus the grid. So here we have grid RC. So this is basically the cell that we're moving to. If there is 0, the cost is going to be 0, and if there is a 1, that is an obstacle, we have to remove it. So this adds a cost of 1. So if the row is the row and column, this is the current cell. The cost of the current cell plus to move to the cost of moving to the next cell, the weight of the edge. If this is less than the cost of the cost of the cell that we're moving to, then we update it and we push the negative. I push the negative of the cost so that it will give the effect of a min heap instead of a max heap. So at the end, we return the cost of reaching the bottom right corner. So that is all for this problem. Well, actually, if you read the hints of this problem, you'll see that they suggest that you can solve this problem with 0-1 breadth first search. That is one special case of finding shortest path on a weighted graph where you have only 2 weights, 0 and 1, which is simpler than this one, but not much simpler. So you can go with the Dijkstra. So in terms of time complexity, 0-1 breadth first search would probably be faster than Dijkstra, because we in this case we're using a min heap where we have a cost of log n to retrieve a cell, a node. But in case of 0-1 breadth first search, we would use a double-ended queue where you can access both ends in O1. So basically, I believe that this is pretty much what you need, because 0-1 breadth first is not much of an intuitive one. I wouldn't say intuitive, you can learn it, but it would need its own video to explain, and it's not as widely used as Dijkstra. Probably not most people know 0-1 breadth first search, so that's why I go for the Dijkstra. Otherwise I have also the code for 0-1 breadth first search. So this is all for this video. I didn't want to keep it too long. I might have talked about the Dijkstra and then move on to this problem, or even discuss this problem into depth. And yeah, I hope this video helped. See you in the next videos.